talk, you might think I'm in the wrong session, but nevertheless, let's start. So my name is Noor, and I'm from RWTH Aachen University. I'm here with my colleagues, Adrian, Wagner, Voelker, and Borchers, and this work was done in collaboration with Jürgen Steimle from Saarland University. And today I will be talking about Springlet. So skin is our natural tactile interface to the physical world. It's unique in the way that it can recognize distinct sensations, such as touch, stretch, pressure, and motion. And in our daily lives, we rely on these sensations and touch gestures to communicate and express our feelings and intentions. To send subtle cues for guidance and warning, and to stay aware of our physical surroundings and preferences. Knowing how rich and expressive our tactile sensory is, we wondered, why don't wearables support touch gestures? Well, the short answer is hardware. For the long answer, let's look at what wearables contain. So most of our wearables already provide some kind of tactile feedback. It is vibration patterns on the skin. And the reason these are very famous is that vibration motors are quite compact. They are easy to integrate in a wearable form. That can be attached on different body locations. But if we're thinking about generating touch gestures, first we need a more sophisticated motor. A motor that is strong enough to actuate and deform the skin, and a mechanical system attached to this motor that can transform this power into expressive movements and forces. And these combinations usually result in bulky, rigid, and complex form factors. And they're definitely more challenging to wear on most body locations, but they're also hard to combine in a single wearable expressive interface. So to answer to these challenges, we developed Springlets. Springlets are the first tactile interfaces to generate a wide range of touch gestures. They come in thin and flexible form factor that allows them to be worn on the skin like stickers. Thanks to the silent operation of Springlets, they can be even worn on near the head and the ear. So to show you some of Springlets' expressiveness, we developed 6 modular interfaces that generate different sensations. I will quickly show you the videos, and I will describe them later when we talk about their design and implementation. So the first interface is our pincher. The second is our directional stretcher. We then have our presser, pushing on the skin. Our puller. Sorry. Our puller. I promise it pulls. Yeah, here. And then we have our expander, which transforms an expandable object, making it larger when it moves. And then our dragger, which has this rigid object that it can shift over the skin. And what makes Springlets unique is that they are all driven using a single type of actuator, and that is the shape memory alloy spring that you see in this picture. Shape memory alloy springs are thin and flexible coils that can contract like a muscle when driven with current and expand when current is removed. As you notice, the movement they generate is quite smooth, yet powerful. If we compare the shape memory alloys to other electromechanical actuators, they would have a higher force-to-weight ratio. So they are lighter in weight to the amount of force they can present on the skin. And they also operate in complete electrical and mechanical silence. So no additional damping mechanisms required. Let's go. Our main challenge in this project was to find out how to transform this simple contraction-expansion movement into a range of expressive touch gestures. But before we talk about that, I would like to acknowledge the related work on tactile interfaces. These are interfaces that can generate sensations such as dragging, tapping, squeezing, and particularly interfaces that already incorporated shape memory alloys either to squeeze the skin or to tickle it. So we have 3 contributions that we will talk about during this talk. How we design springlets, how we fabricated springlets, and eventually are springlets really working? So the evaluation of them. Let's start with design factors. So we're going to show 4 design factors that help transform the simple shape mirror alloy springs that you just that you just seen into expressive springlets. The first one is physical attachment techniques. And by that we mean the way an SMA is attached on the skin. We identified 2 techniques. In the first one, the SMA is directly attached to the skin. So when it moves, it actually actuates the skin under it. For some reason, my transitions are not working for me. Okay. This is our pincher interface that we saw earlier. The second attachment technique uses an additional object, a haptic object. It can be a rigid object or a soft object. It can be large or small. And the idea is, when contraction happens, contraction causes the object to transform, either by changing its shape in one form or another. And this technique in particular expands the design space of springlets. Imagine the type of objects that you can attach and the type of transformations you can achieve with a single contraction expansion. The second design factor is bias force. And bias force is necessary when working with SMAs because they can contract with current, but when they relax super slowly. So you do need a resistant force to pull them back to their stretched length to allow repeated contractions. In springlets, bias force also contributes to the distribution of force on the skin. So in this example, we have one point of this interface larger than the other. So one attachment point is larger, which means that the bias force that the skin elasticity is causing at one point is larger. So the SMA will easily contract and stretch the other point, creating a directional stretcher. Another source of bias force can be the attached object itself. So in this example, we're using a bendable object. During contraction, it pushes the skin, and during expansion, it is responsible for expanding and pulling the spring back to its elongated form. But what if the attached object is not elastic? Well, in this case, and this is our expanding object, we just embedded it with a simple passive spring. So the spring will help pull the SMA back to elongation. Alternatively, we can use an active spring. For example, another SMA. Here we're connecting the object with 2 SMAs instead of 1, and this allows us to have better positional control and bidirectional control. Our third design factor is angle. So this means the angle between the SMA and the skin, and the SMA and the attached object will influence the force vectors on the skin. So in this illustration, we manipulated the angle in order to split the single force of stretch into 2 force vectors. One is normal and one is tangential. In this case, that also means that the friction of the skin is now a bias force that is working against us and should be considered in design. Finally, our fourth design factor is the dimensions of the SMAs themselves. Simply put, if you have a bigger SMA, one with a larger diameter, it will give you larger force. If you have a longer SMA, it will give you larger displacement. In the first example, we're using a larger SMA that is 1.5 larger in diameter than in the dragger example, but it generates 3.5 times the force. Both of these SMAs contract to 50% of their elongated length during actuation. So a longer SMA definitely translates the object further. Okay. So our next stop is fabrication. How did we implement these design factors into a physical form factor? And And we'll talk about Springlet's design and sticker structure, but before that, we set to ourselves 2 goals. This structure needs to be effective and efficient, so the Springlet should be able to use all the power that an SMA provides to actuate the skin or an object on the skin. And the structure needs to be ergonomic. We developed a 3-layer structure. In the first layer, the enclosing layer, we use it only as a protection. So it protects the user from the SMA and the SMA from the user. And this layer is made of silicone rubber. This is the same material that we're using in our baking forms, so it's very skin-friendly and stretchable and heat-resistant. And that's important because the SMA do heat up quite a bit, up to 70 degrees Celsius, when contracted. The second layer is our tactile layer. This is where our objects and our SMAs will live. And the shape of this layer determines how large that Springlet is and how it's going to be attached to the skin. The final layer is the attachment layer. And for that, we use kinesio medical tape. It's very stretchable and breathable and super thin. And it also can withstand the heat of the SMA, but it cannot prevent it from reaching the skin. So we did add a layer of heat barrier. Overall, if we stack all these together, we'll get a 3 millimeter thick Springlet, assuming a 1.4 millimeter SMA inside, and a very flexible shape. Okay, I will let this video run. You need to focus on it. But what I would like to highlight here is the limited number of materials that we need and tools to generate a Springlet. Any of our Springlets that you already saw took around 15 minutes of work and less than $6 to build, including the cost of the SMAs themselves. What we're trying to communicate here is that Springlets provide a unified platform for generating a large range of interfaces. And these are modular interfaces. We'll talk about combining them in a bit. So evaluation. Are Springlets actually working? Well, I would first invite you to come test them in our demo, but before you do, I'd like to show you some numbers. So we had a within subject study with 10 participants, 3 female, and we asked them to wear 3 Springlets. These are representative Springlets. We have one that stretches the skin, one that pushes, and one that transforms an object on the surface. They place these Springlets on 6 body locations of different curvatures, sensitivities, and elastic resistance. And we asked them to test these Springlets while they're sitting down and while they're standing. So we got around 1,000 data points, and the results are as following. In terms of noticeability, we got an average above 4 on a 5-point Likert scale, showing that pincher is the most noticeable, followed by the dragger and the presser. I know you have a lot of questions about this graph, and I have a lot of details in my paper about that, so I will skip this here. What's interesting, though, is that mobility did have a significant effect on noticeability. The Springlets were less noticeable while moving, but the effect size was so small that we were happy with the result already. In terms of expressiveness, what data tells us is that if a user finds a Springlet to be noticeable between 4 and 5 on a 5-point Likert scale, they are 73% more likely to figure out the right sensation it produces. This breaks down, however, if the interface or the Springlet is not mounted correctly on the skin. Simply put, imagine the dragger or the presser or any of these Springlets attached on body hair. If they're not completely adhered to the skin itself, they will pull the hair. They will be painful and they will feel more like a stretcher, and that's what exactly happened in our study. Okay, in terms of wearability, we asked users, are they obtrusive, are they easy to wear, are they lightweight? And for all of these answers, we got a positive reply. The average was 4.2 on a 5-point Likert scale in terms of comfort. Some users thought that they almost forgot that they were wearing springlets. We had 2 exceptions for this rule. Especially for our male users who had body hair on the chest and the back, they did rate some of springlets to be painful when they pulled on the hair. One solution to overcome this is to just use better adhesive. Kinesio tape is good, but on body hair it is challenging. The females in our study, however, thought that having a springlet on the chest actually felt like wearing a necklace, so it was quite enjoyable. So finally, we had one user, curious user, who wanted to see springlets after the study because they weren't actually allowed to see them during the study, and she thought that they looked good on her. So we were happy to know that they're also aesthetically pleasing to some people. Okay. So our last station is application. I will go very, very quickly on 4 applications, and I will leave the rest for you to read in the paper. So the first one is our intimate messenger, a basic structure, pulling on the air loop in different force values. The silence and the smooth movement of Springlet allows us to create this kind of intimate interfaces for enjoyable events. The second one is our breather coordinator. The physical object here, the zigzag, is trying to mimic the expansion and the contraction of the chest. So it will tell people how to inhale or exhale in a shallow or a deep breathing mode. Our navigator is an example of how you can easily combine modular springlets in a single spatial interface, creating a natural mapping for directions. And finally, our virtual reality backpack is just 3 pressors distributed on the shoulder where your backpack would usually tug. And we map the virtual waves to dynamic pressure on the shoulder. In our paper, we have also examples of off-skin applications where we're still working on these, but they're interesting as first insights. Okay, so in conclusion, today we talked about springlets, which are the first tactile interfaces to generate a wide range of expressive touch gestures in a thin and flexible form factor. We showed how highly flexible they are, how customizable they are, and how easy it is to combine them and to control them using current. That concludes my talk, and I am happy to receive your questions.
We have 2 minutes for the questions. If you have any question, please come here and speak in the mic.
Oliver Schneider, Waterloo. Great work. So when you looked at expressivity, you looked at different physical devices, right? Whereas in your application areas, I saw that you're varying the signal, like speed and different amplitudes and such. What kind of expressivity can we expect from the different input signals to a given springlet? So how much expressivity do you have if you have a single thing on your body and you want to play around with different signals?
Right. So we do have control over force profiles. You either can control the force of a single springlet, as a main springlet, or you can use parallel springs, so you can get a wider range. You can also control movement. So just by cutting the current earlier, you can make them stretch less or more. But beyond that, the most expressive part of this is the ability to join more than one modular springlets in one interface, like we showed in our navigator example.
And quick follow-up, do you have closed loop control or is it all open loop?
Yeah, that's future work.
Okay.
Well, thanks again for your amazing talk.